Hey guys, this is chapter 6 of 1211. We are starting to look at electronic structures. This section is a pretty significant change from the previous work we've been doing. Chapters 3, 4, and 5 are all about mole calculations and stoichiometry and all that stuff. Now we're going to go back to some topics that we touched on in chapter 2, talking about the structure of the atom. We learned about protons, neutrons, electrons, but then we kind of left off. We didn't really fully explain what the electrons were doing. They are somehow flying around the nucleus. They're held in orbit by the attraction between the negative charge of the electrons and the positive charge of the nucleus, but we really didn't elaborate on any of the science or the discoveries that were involved in how that works. Most of this information was discovered during the 1900s. Between 1900 and say 1960 or so. So we're going to break it down. I will say a lot of the section will get into chemistry. A lot of this fundamental stuff is based in physics, specifically theoretical physics. So if you hear about guys like Einstein and Schrodinger and Niels Bohr and all that, those are the guys that kind of laid the foundation of this. They were really more physicists than chemists, but there are places where you can't really separate the two. Okay, so overall, what we're trying to get to is this idea that electrons and how electrons of one atom and the electrons of another atom, how they interact with each other, controls many of the properties that we observe when we study different elements and compounds and how they interact and why they behave the way they do. So the foundation of this that we have built in the past 100 years is quantum mechanics, but there's a lot of lead up that we need to go through to get to quantum mechanics. When it gets to quantum mechanics, there's some really deep high level math involved with that. We're only going to touch on the surface of that and just get an idea of kind of the overall concept of it, but we are going to go through some of the math that led up to that discovery. Okay, so in order to do this, we need to really start out with looking at different types of light, which light is electromagnetic radiation. We need to study the properties of light and the how to do some calculations with a photon of light. This is important because essentially this is the point where in the 1900s, Einstein was one of the ones that came up with the idea that light is not purely a wave. It also has properties that make it behave more like matter. So that's called the dual nature of light, that it behaves both as a wave and as a particle at the same time. If light does that, then when we get down to tiny subatomic particles like electrons, we realize that they actually also show properties of matter, because electrons are a small particle of matter, but they also show properties of waves. Okay, so we need to understand the basic structure of how waves work. So that's what the next few slides are. When we look at waves, again, there's more to waves than what we're going to talk about. If you take a physics class, you'll go a lot more in depth. But our three main characteristics that we need to talk about, first of all, the wavelength. If you draw a wave out, how it goes like a sinusoidal wave, the distance from the crest of one part of the wave to the next crest when it goes through one cycle of the wave, that distance is called a wavelength. Again, if it's a distance, then our base unit for that is going to be meters, but depending on what kind of light we have, sometimes it will be converted into other versions like centimeters or micrometers or nanometers, or even another unit called angstroms, which angstroms are 10 to the minus 10 meters. But anyway, so wavelength is a unit of distance. It's the distance between two peaks in a wave. Then we have frequency. The idea of frequency is it's the number of wavelength cycles that pass by a given point per second. Visually, I think about this like if I'm standing at a train station and a train's driving by real fast, if I sit and count how many train cars go by in a given amount of time, that would be the frequency of the train. Okay, so let's say the train's going by and over a minute, I count 30 cars passing by. So that would be 30 cars per minute. That's the frequency. Now, when I'm dealing with a wave, instead of a train car, each unit is going to be one cycle of the wave, from the top of one peak till it comes back to the top of the next peak. So that's one cycle. If I count how many cycles go past per second with light, it's going to be a really big number because light travels extremely quickly, but the frequency is that value. Okay, now they're going to be related to each other, the wavelength and the frequency, by the speed of light. We consider the speed of light, this is a measured value that with 5 sig figs, it's 2.9979 times 10 to the 8th meters per second. Now, often that'll be rounded off. If you round it to 3 sig figs, that's going to be 3.00 times 10 to the 8th. If we get a little lazy, sometimes we might say 3 times 10 to the 8th. Okay, but that's still actually accurate to 3 sig figs if you just put the zeros on there. Okay, so typically on these calculations, we're mostly going to keep 3 sig figs, maybe 4 or 5 if necessary, but just go by the numbers that are in the problem. Keep in mind the speed of light, you should have at least 3 sig figs in your speed of light. Okay, so with those values, again, next couple of slides kind of repeat what we said. The frequency, the units that we use, because we're counting how many cycles per second will pass by a given point. Cycles is just a number, so on the top there's not really an actual unit value there, so sometimes it'll just be written as 1/seconds. It could be 50 per second or 100 per second, but the unit is just per second. And then if we have per second, any value that's in the bottom of a fraction, you can also write it with a negative exponent. So seconds to the -1 is the same thing as 1/seconds. Again, sometimes we'll say per second to represent either one of those. And then finally, the units of frequency were given kind of a proper name of hertz. Okay, so if we talk about the frequency, we could say 50 cycles per second, or we could say 50 hertz. Those are equivalent to each other. Now, if you listen to the radio, if you listen to FM radio, when you turn the station, you're adjusting the frequency that your radio is receiving. So if you listen to 97.1 is your radio station, if you like to listen to oldies music, that is 97.1 megahertz. Okay, now in chapter 1, we learned the prefixes, so you should know mega means 10 to the 6th. So if it's megahertz, that means it's 1,000,000 times bigger than the base unit of hertz. Okay? Anytime we do calculations in this section, whether it's wavelength or frequency or anything else, we always need to convert everything into the base unit before we start plugging into any of the equations that we're going to use. Okay? So our equations, there are going to be a few of them that we're going to need to know. First one relates frequency and wavelength. Now actually I'm going to slide over my board. On this board are all the equations that we're going to need to know. So the first one, the way I usually write the equation if I'm writing it down on paper, speed of light is letter C, equals the wavelength is lambda times nu. Okay, that equation is the same one that's on the screen, it's just the one on the screen has been rearranged to solve for the frequency. Doesn't matter which one you know, you need to have that equation handy whenever you need it. Then we're also, on the next slide or two, we're going to introduce energy. When we have a photon of light carries a certain amount of energy, we can calculate the energy from the frequency. The equation would be the energy of a photon equals H is going to be Planck's constant. We're going to see that in a minute. And then again, nu is a curved V. It's like a cursive V. It's from the Greek alphabet. That is the frequency. So Planck's constant times the frequency will give me the energy. Or if the problem gives me the wavelength instead of the frequency, we can do some substitutions and we can get this equation where the energy of a photon equals Planck's constant times the speed of light divided by the wavelength. Okay, so it's nice to have both of those because sometimes the problem will give you the frequency, sometimes the problem will give you the wavelength. Either way, we got to be able to get to the energy of a photon. Okay, and then when we start looking at electronic transitions, again, this is a little bit ahead of us, but we're going to use the Rydberg equation where the wavelength is related to N1 and N2 are the energy levels that an electron can exist in. Again, we're going to cover those problems in a little bit, but this shows all the equations for this section that you're going to need to know. They're on the formula sheet, which is in the shared class files or on D2L, but when you take a test or do homework, make sure you have all these equations handy so that you can decide which one the problem calls for and start working it out. All right, so if I keep moving, when we talk about electromagnetic radiation, that's the big fancy scientific term for light. There are all different kinds of light that are around us all the time. Actually, of all the light that's traveling through this room right now, my eyes can only see a tiny fraction of the overall light that's present. Okay, so if I look up on this scale, visible light represents a tiny little segment here, and actually this is enlarged to be a much larger fraction of the total light on the scale than it should be. It should be a very, very narrow slit right there. But if I take visible light, pass it through a prism, then what I'll see is it can be spread out and I see the whole rainbow, Roy G. Biv, where if I start on the red side, red, orange, yellow, green, blue, indigo, violet, that's my color scheme. You need to know that. As I go through this, on this scale up here, again, all of this fits into that little sliver. But if I go beyond violet light to the left, I'm increasing the energy. So above violet in energy is going to be ultraviolet. Ultra means above. So I go from visible light, I go past purple, going left, I get to ultraviolet light. If I go beyond that, then I get to X-rays and gamma rays. That is increasing energy. Once you get above ultraviolet light, that's what we call damaging radiation, where it can cause, when it hits an atom, it can cause electrons to fly out, and if that happens in your skin, it can cause reactions and bad things to happen, which can cause cancer and stuff like that. So these are the dangerous radiation types over here. And then on the red side of visible light, if I go below red, I get to infrared. Infra is a prefix that means beneath. So I have infrared, microwaves, radio waves. It would be a really good idea for you to have a good idea of all these types of light in your head, kind of have an idea of how they're related to each other. So as I go to the left, the energy is increasing, but if I look above the scale, the wavelengths as I go left are actually decreasing. Wavelength and energy are inversely proportional. Okay, if I look at my equation, that should make sense. I have an equation right here, E equals hc over lambda. Lambda is the wavelength. If this number gets smaller in the denominator, if I divide by a smaller number, it's going to make the energy get bigger. So wavelength and energy are inversely proportional to each other. Now remember the top two things, the H and the C, those are both constant values, so they don't change. Okay? But if I change the wavelength of light, it will affect the energy that one piece of that light will carry, which we call one piece of light a photon. Okay? Then if I look at frequency, if the frequency is increased, make this number bigger, multiply it by Planck's constant, it's going to make the energy get bigger. So frequency and energy are directly related. If the frequency goes up, the energy goes up. If the wavelength goes up, the energy goes down. As I said a minute ago, they're inversely proportional. So then if I look at frequency and wavelength, if the wavelength goes up, the frequency has to go down, because when I multiply them, they have to equal a constant. So if the change in one of them, it's going to have to be mirrored by the other one in the opposite direction. So when you multiply them together, you'll still get the same answer. Okay, so you do need to know those relationships between wavelength and frequency and energy, know which ones are directly related, which ones are inversely related. Okay, that's just kind of basic information that we have to have straight in our heads before we can really attack all the problems that we're going to do. Okay, so if we look at the scale, gamma rays, the wavelength of gamma rays can be smaller than 10 to the minus 11th meters. So we're talking smaller than the size of the nucleus of an atom. We're getting on the scale of like below angstroms into like picometers and stuff like that. So the wavelength, the distance between one wave and the next, is so tiny that it can't be seen. And then on the other end, if we get to radio waves, when we calculate the wavelength of radio waves, they can be on the order of whole meters to even hundreds of meters longer than football fields. Okay, so the range that we're covering with electromagnetic radiation is tremendous. These have a huge amount of energy with each photon. These have a tiny amount of energy with each photon. Okay, I'm going to go ahead and cut off this video and we'll continue in the next one.